Welcome back, deep divers. Have you ever paused to consider the unseen infrastructure that powers the smart in your latest AI application or, the sheer computational muscle behind every generated image or piece of text? Today, we're embarking on a deep dive into a topic that's been humming louder than a server farm: artificial intelligence and its truly incredible and rapidly growing appetite for energy.
Yeah.
It's a story of fascinating paradox, really. Massive consumption, but also some remarkably innovative solutions that are already beginning to reshape our energy future.
That's right. For this deep dive, we've pulled together, well, quite an extensive array of sources. We're looking at granular scientific reports, detailed energy analyses from powerhouses like the International Energy Agency, MIT,
Right.
crucial government insights, say, from the U.S. Department of Energy, and also forward-looking industry perspectives from leaders like Goldman Sachs and McKinsey.
Okay.
Our mission today is to thoroughly unpack this critical nexus, to understand not just how AI is creating this, frankly, unprecedented energy challenge, but also, and maybe this is counterintuitive, how it's also emerging as an indispensable tool for revolutionizing our entire energy ecosystem, potentially propelling us towards a more sustainable future.
Okay, let's unpack this then. You've likely caught glimpses of headlines about AI's rapidly expanding footprint.
Oh, yeah.
We're going to dive deep, get to the bottom of just how significant that footprint truly is, explore the ingenious ways innovative minds are working to, shrink it,
Right.
and then reveal where AI itself is stepping up to help us build a more resilient and sustainable energy landscape. Prepare for some truly surprising developments, because we're about to uncover some insights that might just change how you think about AI and energy.
All right, to truly grasp the scale of what we're discussing, let's start with the sheer magnitude of the challenge. I mean, we're talking about an industry that depends entirely on these massive data centers.
Entirely, yeah.
And the energy demands of these digital factories are just, well, skyrocketing. What are the numbers telling us about this burgeoning appetite and, what are the immediate implications? Well, what's truly fascinating here, and frankly, quite sobering, is the sheer velocity of this growth. The data centers that form the backbone of our entire digital world, especially now with the exponential rise of AI, they're consuming a rapidly increasing share of global electricity. According to the International Energy Agency, IEA, these facilities could consume a staggering 3% of the world's electricity by 2030.
3%.
Yeah, 3%. And that's double what they use today, which, is already comparable to the energy consumption of a country like Germany.
It's just for data centers.
Just for data centers.
Yeah.
Now, if we narrow that focus down to the United States, MIT Energy Initiative projections suggest this demand could rise even more sharply, potentially reaching, get this, an astonishing 12 to 15% of the nation's total electricity by 2030.
15% just from data centers, largely AI.
Largely driven by AI's rapid expansion, exactly. And other global estimates, like those from the Brookings Institution, they paint an even more dramatic picture. They suggest that worldwide data center consumption, fueled primarily by AI, could reach as high as 21% of global electricity by 2030.
21%.
Wow.
These figures aren't just abstract statistics, are they?
Not at all.
They truly represent a profound and significant challenge to our existing power grids. I mean, these grids weren't fundamentally designed for this kind of explosive, frankly, unforecasted growth.
No, they weren't.
This necessitates urgent solutions, doesn't it? Not just for grid stability, but also to prevent these demands from basically derailing our global climate goals if we don't get a handle on it.
Precisely. And it's important to understand that it's not just the data centers as these monolithic entities. It's the individual AI models themselves that are incredibly energy intensive.
Right, you mentioned ChatGPT in our notes. Can you break down the energy hunger of these specific models? Are there particular examples that truly illustrate just how hungry these digital brains are?
Absolutely. These individual AI models are incredibly resource intensive. They consume vast amounts of electricity, not just during their operational use, but critically during their incredibly demanding training phase.
Ah, the training.
Consider this. Researchers from Google and UC Berkeley estimated that merely training OpenAI's foundational ChatGPT-3 model, just training it, consumed enough electricity to power around 120 average U.S. homes for one entire year.
For one model's training.
For one model's training run. And for its successor, GPT-4, that demand likely jumped by an astounding 50 times.
50. 50 times.
Oh.
It's such a huge jump.
Well, increased complexity, much larger data sets, just the sheer scale of the model. To put it into a context many of us can maybe relate to,
Yeah.
one estimate suggests that a single query to ChatGPT, generating a relatively short response,
Yeah.
uses nearly 10 times more electricity than a normal Google search.
10 times more per query.
Per query. Now imagine if Google were to process, say, 9 billion AI-powered searches a day,
Yeah.
which seems plausible as AI gets integrated, right? That daily volume would require an estimated 23 to 30 times the energy of normal searches. It's a truly immense and, frankly, potentially unsustainable leap in demand.
Okay, so that's text. What about images or video?
Good question. The energy drain isn't just for text. The MIT Technology Review highlighted that generating a mere 5-second video, for instance,
Just 5 seconds.
just 5 seconds, uses about 3.4 million joules of energy. That's comparable to running a microwave oven for over an hour.
For a 5-second video clip.
Yeah.
Wow.
Yeah. This underscores a fundamental relationship, as OpenAI CEO Sam Altman presciently noted, that the cost of intelligence will inevitably converge to the cost of energy. The critical insight here, I think, is that the unprecedented scale and computational intensity of advanced AI models aren't just driving up demand incrementally, they're fundamentally shifting the economic and environmental calculus of digital innovation.
So it's clearly not just about the electricity consumption, is it? We often overlook other critical resources that go into powering these digital brains, things that might not immediately come to mind when we think of computing.
Right.
What are these hidden indirect costs?
This raises a profoundly important question for understanding the full environmental footprint of AI. What are these hidden costs beyond kilowatt hours? Well, beyond electricity, these systems require massive amounts of water for cooling, just to prevent the servers from overheating.
And we're not talking small amounts, I gather.
No, not trivial amounts at all. Some UK researchers, for example, estimate that global water use for data processing could reach half of the country's entire water usage by 2027.
Half of the UK's water per year.
We're protesting.
Yeah, it's a truly staggering projection for a single sector, comparable to supplying the entire population with drinking water. MIT News offers a simple yet powerful analogy to make this tangible. Generating a single image with AI consumes roughly the equivalent of an entire bottle of water just for cooling purposes. A bottle of water per image.
Okay.
But the footprint extends much further. We also need to consider the substantial energy used to construct and maintain the large building infrastructures that house these data centers.
Right, the physical buildings.
Exactly. As well as the embodied energy in the computing hardware, the storage systems, the networking equipment themselves, from the mining of rare earth minerals to the complex manufacturing processes.
And then disposal.
And then there are the significant end-of-life costs. Absolutely. A graphics processing unit, a GPU, which is the indispensable workhorse of AI, is typically used for only about 4 years before it's either discarded or repurposed. There's currently very little transparency on the environmental impact of this growing mountain of electronic waste. It leaves us with a significant unknown in the overall sustainability equation. So the key insight here is that AI's impact is a holistic environmental challenge.
Yeah.
It touches on energy, water, raw materials, and waste, making it a far more complex problem than just reducing electricity bills. That's a truly comprehensive picture, and honestly a bit sobering. It highlights that the impacts are far broader than just what we see on our electricity bills.
Definitely.
But I've heard about continuous efficiency gains in AI hardware and software. Shouldn't those help mitigate this growing consumption? Or is there, a catch that we're missing?
You're touching on what's known as Jevons paradox. It's a phenomenon first observed way back during the Industrial Revolution.
The steam engine one.
Exactly. The invention of the more efficient steam engine paradoxically led to increased coal consumption, not less.
Right, because it became cheaper and more useful, so people used it more.
Precisely. The paradox suggests that while there are indeed genuine continuous efficiency improvements in AI hardware and software, meaning individual AI tasks, might use less energy per computation over time. These gains can actually lead to increased overall resource consumption rather than a decrease. The logic is, as you said, lower energy costs for AI systems make them cheaper to run, which in turn generates greater demand, broader adoption, more intensive usage across an ever wider array of applications and users.
So you get this rebound effect.
Exactly, a powerful rebound effect. So even as each individual AI model or data center becomes more efficient, the sheer proliferation and intensity of AI usage could still drive up total energy consumption dramatically. The critical insight from Jevons paradox here is that efficiency efficiency alone, while absolutely necessary, may not be sufficient to curb total energy demand. We can't simply innovate our way out of the problem without also addressing the underlying drivers of demand and consumption patterns.
And it seems like these impacts aren't just abstract global numbers. They're not felt equally, are they?
No, absolutely not.
While we talk about global statistics, there are very real, tangible consequences playing out in specific communities, particularly where these data centers are concentrated. What are we seeing on the ground?
This is a critical aspect indeed, and it points to significant environmental justice concerns. The impact of increasing energy demands and the physical presence of data centers will not be felt equally across all regions and populations.
Yeah.
Virginia's Data Center Alley, for instance, serves as a really stark example. This region hosts over 300 data centers. It's the largest concentration in the U.S., processing maybe 70% of the world's internet traffic.
Wow.
Residents there are actively fighting continuous expansions due to very tangible concerns. Not only rising energy bills as utilities struggle to keep up, but also increasing water demand in already strained regions and worsening air quality from the exhaust of backup diesel generators that often kick in during peak demand or grid outages.
Diesel generators.
Yeah. And furthermore, we've seen a high-profile case recently where the NAACP sued Elon Musk's xAI, alleging that it operated turbines for a South Memphis data center without appropriate permits, directing toxic emissions toward predominantly Black neighborhoods. This case specifically highlights grave concerns about environmental racism, where communities of color disproportionately bear the brunt of industrial pollution and environmental degradation, often lacking the political power to resist.
So it's not just abstract energy problem, it's very much a social justice issue too.
Exactly. The rapid growth of AI infrastructure isn't just an abstract energy problem, it's a very real social and environmental justice issue with direct, unequal impacts on local communities and vulnerable populations.
Okay, so we've clearly identified the problem. It's massive, it's complex, it has a lot of moving parts and significant consequences. But where do we go from here? Are companies and researchers just throwing up their hands in despair, or are there, as one expert put it, clever solutions being developed to tackle this monumental challenge?
Oh, absolutely not throwing their hands. This is precisely where innovation steps in with incredible agency and ingenuity. Mosharraf Chaudhary, he's a University of Michigan professor researching efficient AI. He highlighted that companies are pursuing a two-pronged approach, basically. The first, and often the most challenging due to inherent timelines, is simply build more energy supply.
Which takes time. A lot of time.
A significant amount of time, yeah. Permitting, construction, infrastructure development. AI giants, recognizing this bottleneck, are already scouring the globe for new, reliable energy sources. Google is even pivoting its strategy to consider investing directly in nuclear reactors to power its AI operations.
Nuclear. Wow, that's a big shift for a tech company.
It's a huge shift. The second approach, and perhaps the more immediate and nimble one, is to figure out how to consume significantly less energy for the same computing power.
Right. The efficiency angle.
Exactly. This is where those clever solutions truly come in, spanning innovations across hardware design, software, and algorithmic optimization, and the operational strategies of the data centers themselves. It's a race against time, but the level of ingenuity is truly impressive.
Okay, let's dig into those clever solutions. What's happening at the hardware level? Because those chips are getting incredibly powerful, and with that immense power, of course, comes a tremendous amount of heat.
Exactly. At the hardware level, we're seeing significant advancements driven by sheer necessity. Modern AI chips, like the latest generations from NVIDIA, for example, consume an astounding 100 times more power than servers did just 2 decades ago.
100 times more.
100 times. This massive power consumption naturally generates immense heat, making efficient cooling not just important, but absolutely paramount.
So what are they doing about the heat? Bigger fans.
Well, much more advanced than that. This challenge is leading many major players to explore and implement liquid cooling solutions.
Liquid cooling, okay.
Yeah, this technology replaces those energy-hungry air conditioners and vast amounts of airflow with a specialized dielectric coolant that circulates directly through the servers, either submerging components or running through cold plates attached right to the chips. It's far more efficient at dissipating heat.
Is it catching on?
Oh, yeah. Gareth Williams from the consulting firm Arup noted that all big players are looking at it because the gains are so substantial. Amazon's AWS, a world leader in cloud computing, has already developed its own innovative liquid cooling method specifically for NVIDIA GPUs in its servers. And crucially, their solution avoids the need to entirely rebuild existing data centers, which would be a massive, time-consuming, and expensive undertaking.
Well, you can retrofit it, kind of.
Exactly. Beyond advanced cooling, there's also continuous progress in just making new generations of computer chips inherently more energy efficient through refined transistor design, specialized architectures for AI workloads, advanced manufacturing processes.
So the chips themselves get better.
They do, and furthermore, research, like that from Purdue University's Ding, has shown that AI chips could potentially last longer without losing performance by running them at slightly lower but still optimal frequencies.
So use them longer.
Potentially. However, convincing semiconductor companies to potentially make less money by extending chip lifespans and thus reducing the frequency of lucrative upgrades is, as Ding noted, a significant business hurdle. Innovation alone can't easily overcome that without policy or market pressure,
Right. The business model gets in the way.
Exactly. The key insight here is that while raw power demands are increasing, radical innovations in hardware, particularly cooling, are essential just to keep pace with AI's thermal output.
So it's not just about the physical components, but also the intelligence behind the operation. The software and algorithms themselves. How are they getting clever in their energy usage?
Precisely. Algorithms and software optimization are playing a huge, often underestimated role in reducing energy consumption. Mosharraf Chowdhury's lab at the University of Michigan, for example. They've developed sophisticated algorithms that calculate exactly how much electricity each AI chip needs at any given moment, rather than just providing a constant maximum power supply.
Like a smart thermostat for the chip.
That's a great analogy. This dynamic power allocation approach alone has been shown to reduce energy use by an impressive 20 to 30%.
Wow, just by being smarter about power delivery.
Exactly. Then there's the fascinating case of this Chinese startup, DeepSeek. They unveiled an AI model performing just as well as top US systems, but, crucially, using less powerful and, by extension, less energy-intensive chips.
How do they manage that?
Well, not through raw hardware brute force, but by programming the GPUs more precisely, optimizing the instruction sets, the memory access patterns, and by strategically skipping an energy-intensive training step, pre-training with massive unlabeled data that was previously considered essential.
So clever programming beat brute force.
Essentially, yeah. It highlights that innovation isn't just about throwing more computational power at a problem, but about smarter, more elegant programming. The key insight is that smarter AI doesn't always mean bigger AI. Clever architectural and algorithmic choices can yield comparable performance with significantly less energy.
Are there other software tricks?
Oh, yeah. Other efficiencies are resulting from architectural design principles, like building smaller, more specialized models for specific tasks. They inherently require less training and inference energy.
Right. Tailored models.
Exactly. There's also pruning, which involves removing unnecessary connections or neurons in a neural network after training. Kind of like a sculptor refining a block of marble, creating a leaner, more efficient model without significant performance loss.
Interesting.
And quantization, which reduces the precision of numerical calculations, say from 32-bit to 8-bit integers. This saves significant memory and computational energy.
Like rounding numbers.
Kind of, yeah. You lose a tiny bit of precision, but the calculation becomes vastly quicker and less resource-intensive, often without a noticeable impact on the AI's final output. These techniques demonstrate a shift towards a more resource-aware approach to AI development.
And what about the data centers themselves? These are massive, sprawling facilities. Are there ways to run those more efficiently, perhaps even using AI to help itself become more sustainable within its own physical housing?
Definitely. It's remarkable, actually, to look at how far data center operations have come in terms of efficiency. 20 years ago, just operating a data center cooling, power distribution, all that infrastructure required as much energy as the servers themselves, a 50-50 split.
Wow.
Today, largely due to a relentless focus on energy efficiency and continuous innovation, data center operations now use just about 10% of what the servers consume.
Only 10% for operations now. That's a huge improvement.
Massive improvement. It frees frees up more energy for actual computing. Many modern data centers now utilize AI-powered sensors and sophisticated control systems to manage temperature, instead of uniformly cooling entire buildings.
Right, which is wasteful.
Exactly. These systems create dynamic specific zones, directing chilled air or liquid precisely where it's needed most based on real-time heat maps and server loads. They dynamically optimize water and electricity use in real time.
AI managing the AI's environment.
Pretty much. A prime example is Google DeepMind. They succeeded in reducing energy consumption in their own data centers by a significant 30% just by using AI to better predict cooling needs before they become critical.
30% savings using AI.
Yep. Their AI anticipates future heat loads based on weather forecasts, server usage patterns, energy prices, and then adjusts cooling systems proactively. Additionally, the very architecture of hyperscale centers those enormous purpose-built facilities run by Google, Amazon, Microsoft. Their immense scale allows for highly optimized, custom-designed infrastructure, from server racks to cooling systems and power delivery that smaller, more generalized data centers simply can't achieve. They can also locate in colder climates, use ambient air for free cooling for part of the year.
So scale brings efficiencies too.
Absolutely. The critical insight here is that AI isn't just a consumer, it's also becoming a powerful internal optimizer, using its own intelligence to make its physical infrastructure more sustainable.
Okay, this next area of solutions really shifts our perspective, and honestly, it's one of the most intriguing parts of this whole story. We've talked about making AI more efficient. But what if AI itself could fundamentally change how we interact with the entire energy grid, like becoming a dynamic partner rather than just a static drain?
Right.
I'm thinking of smart demand management, something completely different from just making the chips or data centers more efficient.
This is truly where it gets profoundly interesting because it represents a paradigm shift in how we view data centers and their relationship with the power grid. For decades, traditional data centers were built with this unwavering, almost religious focus on maximizing uptime, prioritizing near-perfect continuous operation above almost all else.
Right, the 5 nines uptime goal.
Exactly. Tier 4 data centers, the most robust category, achieve that almost mythical 99.9995% uptime. That's only 26 minutes of downtime annually. This was driven by the critical need for absolute reliability in things like enterprise databases, financial transactions, traditional cloud computing,
Where every second counts.
where every millisecond could mean lost revenue, compromised data, critical system failures. However, AI computing is ushering in a significant regime change, as Goldman Sachs aptly puts it.
A regime change. How so?
Well, for AI companies, particularly in the rapidly evolving generative AI space, speed and scale to market now matter far more than achieving that final fraction of a percent of uptime.
Getting the models out fast is more important than perfect reliability.
Precisely. The competitive advantage lies in quickly deploying the largest models, attracting users, gaining critical data, iterating rapidly to fuel the next generation of AI development. In fact, current AI services from companies like OpenAI and Anthropic are already operating at uptime levels comparable to the lowest tier of traditional data center infrastructure.
Really? So they tolerate more downtime already?
They do. The critical insight here is that AI's unique operational flexibility fundamentally redefines the traditional imperative of always on, opening up entirely new possibilities for grid interaction.
Okay, so AI has fundamentally different priorities, a distinct tolerance for downtime compared to traditional applications. But how does this inherent flexibility actually translate into practical energy solutions? Why is AI uniquely positioned for something like curtailment, which essentially means voluntarily reducing power usage during peak times?
This is truly the flexibility revolution that AI ushers in, and it's a powerful one. AI workloads are surprisingly adaptable, much more so than the traditional transaction-based computing that dominated data centers for decades. Let's consider AI training first, that intricate, computationally intensive process.
Yeah, the one that takes weeks or months.
Exactly. Those operations can actually pause and resume using checkpoints, much like you would frequently save a complex document draft before closing your computer and returning to it later.
Okay, so you can stop and start training.
You can. This means that AI training can be temporarily paused during periods of high grid stress, then seamlessly resumed when power returns to a more stable or cheaper state. Even more remarkably, these training tasks can often be redirected to another data center in a different geographical region where capacity is more readily available, maybe renewables are more plentiful.
So you can pause it or even move it somewhere else mid-task.
Potentially, yes. This ability to halt and restart without losing progress or even to migrate mid-task is a game changer for active grid management.
Okay, that's training. What about when we're actually using the AI, like asking ChatGPT a question? That's called inference, right?
Right, LLM inference. Here, the computational intensity means that the time it takes for the AI to think and generate a response, not network latency, is the primary constraint.
Meaning the AI calculation takes longer than the internet signal travel time.
Exactly. Let's take ChatGPT again. It can take anywhere from, say, 10 to 30 seconds to generate a detailed response.
Right.
Now, consider a user in New York querying a data center all the way across the globe in Tokyo. That might involve approximately 170 milliseconds of network delay, round trip. Now, that 0.1 second delay would be absolutely devastating for traditional web applications. Studies show it can mean an 8–10% drop in sales conversions, users just abandoning the site.
Right, we expect websites to be instant.
We do. But for an AI generating a 20-second response, that 170 millisecond delay is, as Goldman Sachs aptly puts it, immaterial.
Because it's tiny compared to the wait time for the AI anyway.
Exactly. This remarkable tolerance for network latency allows AI applications to dynamically load balance across continents. They can route computational work and its associated power demand to access cheaper power and available grid capacity wherever it happens to be, without sacrificing the user's perception of performance.
So you could run my query in Iceland if the power is cheap and green there, even if I'm in London.
Potentially, yes. And this flexibility becomes even more pronounced with agentic AI systems. These are designed to perform multi-step, complex tasks that can run over tens of minutes or even hours autonomously. In those scenarios, even minutes of network delay become negligible compared to the total computation time. The profound insight here is that AI's unique operational characteristics, its pausability, resumability, latency tolerance, fundamentally transform it from a rigid energy consumer into an incredibly flexible and responsive load, a truly novel concept for grid management.
So this inherent flexibility means AI data centers aren't just rigid energy guzzlers. They could actually become an asset to the grid, almost like a responsive, intelligent component. Tell us more about this curtailment idea and how it works to unlock capacity that already exists.
That's precisely the revolutionary potential. The inherent flexibility of AI workloads enables two significant breakthroughs for our energy system. First, AI companies can proactively and temporarily reduce their demand during periods of peak grid stress, essentially shedding load when the grid is most strained.
Turning down the power voluntarily.
Voluntarily, yes. Second, and equally important, they can load balance across a much larger geographical space, dynamically routing computational work and its associated power demand to wherever grid capacity is most available and perhaps cheapest at that moment.
Okay.
The U.S. power grid, like many others globally, is fundamentally built to meet peak demand, think the hottest summer afternoon, coldest winter morning.
Right. Worst case scenario planning.
Exactly. This planning strategy means that huge swaths of power generation and transmission infrastructure sit idle most of the time, representing significant latent capacity. Curtailment offers a revolutionary way to unlock this existing but often unused slack capacity quickly and efficiently. It effectively transforms AI from a potential grid burden into what Goldman Sachs famously calls a shock absorber.
A shock absorber for the grid. I like that.
It helps stabilize the system, integrate renewables, and avoid costly infrastructure upgrades. The key insight is that AI's flexibility isn't just an operational convenience. It fundamentally changes the economic and technical relationship between computing and the grid, moving towards a truly dynamic and optimized system.
That's a powerful analogy, a shock absorber. How much slack capacity are we actually talking about here? Can this approach really make a significant dent in the rapidly growing demand, or is it more of a theoretical benefit?
Oh, it absolutely can, and the numbers are quite compelling. A recent groundbreaking study by Duke University's Nicholas Institute specifically quantified this opportunity, revealing a truly significant amount of untapped capacity.
Okay, what did they find?
Their analysis showed that a substantial 76 gigawatts, GW, of new load capacity could become available across the U.S. power grid with just 0.25% curtailment. That means the data center would still maintain a very high 99.75% uptime, virtually unnoticeable to users.
76 gigawatts is huge.
It is, and this scales up even further to an impressive 126 GW of capacity, with only a 1% curtailment, which still represents a robust 99% uptime.
So over 100 gigawatts potentially available just through flexibility.
Exactly. To put that in perspective, this could effectively add over 10% to the nation's entire effective grid capacity without building any new physical power plants or transmission lines, simply by optimizing and utilizing demand intelligently.
Wow. And are these long shutdowns?
No, the study found that these curtailment events where power is temporarily reduced are typically quite short, averaging between 1.7 to 2.5 hours. And even during these periods, the data centers often retain high load levels, 88% of those curtailment hours still running at least 50% of their normal capacity.
So it's more like dimming the lights than turning them off completely.
That's a good way to think about it. It's smart, surgical, flexible management that leverages existing resources more effectively. The critical insight is that this flexibility means AI isn't just demanding more power, it's offering a new kind of grid stability and efficiency that could be invaluable for our energy transition.
This sounds like a genuine win-win-win situation across the board. What are the broader benefits of this approach, not just for the tech companies running the AI, but for utilities, and crucially for us, the ratepayers, who ultimately bear the costs of grid upgrades?
The benefits are truly compelling and cascade across the entire energy ecosystem, profoundly impacting all stakeholders. For tech companies, it means dramatically expedited time to market for their AI services and infrastructure.
How so?
They can bypass lengthy grid interconnection backlogs that, for traditional projects, can stretch over 4 years, sometimes even up to 10 years, as utilities struggle to keep up.
10 years just to get connected.
Yeah.
Wow.
It also helps them avoid costly delays in acquiring critical equipment like gas turbines for new power generation, which currently have backlogs extending to 2029 or later. So for them, it's about speed and competitive advantage.
Okay, faster deployment. What about costs?
Economically, unlocking that estimated 100 GW of latent capacity through intelligent curtailment represents approximately $150 billion worth of additional powered infrastructure that can be leveraged today without new capital investment rather than waiting decades for new plants.
So we use the existing grid better, saving huge infrastructure costs.
Precisely. For utilities and ratepayers, it directly addresses a fundamental economic challenge: the chronically low utilization of our existing grid infrastructure. Most of our grid operates at roughly 53% capacity over the course of a year.
Only about half capacity on average.
Roughly, yeah. Meaning billions in fixed assets sit idle much of the time. Flexible AI workloads allow utilities to amortize these fixed costs over more load, effectively reducing per unit costs for all ratepayers without adding strain during those crucial peak demand periods.
So everyone's bills could potentially be lower?
Potentially, yes, or at least rise less quickly than they otherwise might. It truly presents a fundamentally different vision for AI's role. Not a crisis for the grid, but that dynamic shock absorber that drives higher utilization from existing infrastructure. And the critical insight here is that this flexibility is especially crucial for the transition from predictable fossil fuels to the more variable, intermittent nature of renewables like solar and wind. It makes the grid more bidirectional, more resilient, and ultimately more optimized for a clean energy future.
And it's also a significant geopolitical angle to this, isn't there? This isn't just about domestic energy efficiency. It plays directly into the competitive landscape on a global stage, particularly in the escalating race for AI leadership.
Yes, absolutely. The geopolitical stakes are incredibly high. Energy access and the ability to rapidly scale AI infrastructure are now seen as a key determinant for maintaining a country's competitive edge in AI.
So energy equals AI power, globally speaking.
In many ways, yes. While the U.S. faces significant grid constraints, backlogs, public resistance, China is reportedly leagues ahead in available energy sources, including a massive and rapidly expanding base of renewables and nuclear power. China's national strategy involves huge, state-backed investments, allowing them to bring new energy capacity online at a pace few other nations can match. This directly translates into a significant competitive advantage for rapidly scaling AI supercomputing centers, often without the same permitting hurdles or NIMBYism that constrain expansion in the U.S. and Europe.
So China can build AI faster because they have the power ready.
That's a significant factor. This makes the ability to quickly access power through innovative solutions like curtailment not just an economic advantage, but a crucial strategic imperative for the U.S. It's about preventing power limitations from becoming a critical bottleneck that could hinder America's position in the global AI race.
Right.
The key insight here is that we are truly witnessing the collision of two core revolutions of our lifetime: artificial intelligence and the global transition to clean energy. How we navigate this intersection, particularly regarding energy access and flexibility, will have profound implications for national competitiveness and future technological dominance.
Okay, so we've explored AI's daunting energy demands and some ingenious ways to reduce them, and even how AI can help stabilize the grid by being a flexible load. But here's the other side of the paradox, the really hopeful part. AI isn't just part of the energy problem. It's also emerging as a truly revolutionary solution for optimizing our entire energy ecosystem.
Exactly.
What specific capabilities does AI bring to the table for making our energy systems more sustainable, efficient, and resilient?
This is the promise side of the equation, and it's incredibly exciting because AI provides the computational intelligence needed to optimize energy systems that are becoming exponentially more complex. Think electrification, digitalization, connectivity, decentralization, all while facing cost pressures. AI can manage this web.
So it helps manage the complexity.
Precisely. Even in traditional sectors, oil and gas companies are already using AI for highly complex tasks like subsurface data processing to find new reserves, sophisticated reservoir simulation to improve extraction efficiency, extend the life of wells, and critical leak detection in pipelines, preventing environmental disasters and saving resources.
Yeah.
Within the electricity systems themselves, applying AI in power plant operations and maintenance could yield potential cost savings of up to $110 billion annually by 2035.
110 billion a year.
From avoided fuels, improved asset management, lower operational costs, predictive maintenance, things like that. Moreover, AI has the ability to unlock up to 175 GW of additional transmission capacity in existing power lines.
Just by using the existing wires smarter.
Exactly. By optimizing their usage, predicting bottlenecks, dynamically routing power. This significantly facilitates greater, more seamless integration of variable renewables like solar and wind, which often struggle with transmission constraints. These aren't minor tweaks, they're transformative shifts. The key insight is AI's power to analyze, predict, and optimize complex dynamic systems makes it unparalleled for managing a modern energy landscape.
That's incredibly significant. It sounds like AI is making our big national energy systems much smarter and more dynamic. But what about more everyday applications closer to home, like in our homes and industries?
Yeah.
Can AI help us save energy there too, directly impacting our daily lives and businesses?
Oh, yeah, absolutely. The impact extends right down to our daily lives and industrial processes, offering efficiency gains that are both substantial and tangible. In industry, for example, AI is being deployed to optimize production processes. The IEA suggests potential energy savings of 8% by 2035 in light industry.
Like manufacturing.
Yeah, electronics, textiles, machinery. Simply by making operations more intelligent, predictive, responsive to demand, AI can manage everything from optimizing motor speeds to scheduling maintenance to reduce unexpected downtime and energy spikes.
Okay, and what about buildings? Heating? Cooling?
Yeah.
That's a big energy user.
Huge. And AI-driven solutions are profoundly enhancing efficiency and demand response in buildings. We're seeing compelling examples like AI-powered control systems continuously optimizing energy consumption. Center, an engineering group, highlights AI's role in developing customized predictive models for consumption.
Predictive models for buildings.
Yeah. They analyze historical data, weather patterns, occupancy schedules, even real-time energy prices to predict demand, detect anomalies to avoid unnecessary expense, and strategically focus investments where improvements are most needed, rather than just blindly upgrading entire systems. Furthermore, AI orchestrates complex energy-intensive systems like HVAC and refrigeration. It dynamically adjusts demand based on a multitude of real-time variables: external weather, internal occupancy, air quality, the building's thermal conditions, on-site solar generation, even fluctuating energy prices.
Wow, juggling all those factors.
Exactly, to ensure ambient conditions are maintained with the least amount of energy possible. This reduces carbon footprints, operating costs, while simultaneously improving comfort and air quality. The key insight is AI brings a level of predictive power and granular control that allows us to manage energy use in real time, moving beyond static, inefficient settings to truly dynamic, optimized environments.
What about our nation's aging energy grid? You mentioned transmission lines, but the whole system is a massive, sprawling, often analog network. Integrating all these new variable technologies like renewables must be a monumental task. Can AI help there too, beyond just being a flexible load?
Indeed, the U.S. Department of Energy is right at the forefront of applying AI to modernize our aging and increasingly complex grid infrastructure. AI is becoming an essential tool for this vital generational upgrade.
How so?
Well, AI-powered predictive tools are helping utility operators anticipate and mitigate grid disruptions caused by increasingly frequent extreme weather events.
Right, storms, heat waves.
Exactly, which cause billions in damage and lost power annually. These tools can also predict and defend against sophisticated cyber attacks, improving overall grid resilience and ensuring a more consistent, reliable power supply.
Hmm.
Crucially, AI also optimizes grid operations for cost effectiveness and minimizes the impact of variable renewable energy generation, solar and wind, by providing vastly improved load forecasting and state estimation, even with limited or missing data.
So it helps predict when the sun will shine or wind will blow, basically.
In a very sophisticated way, yes, allowing grid operators to quickly adjust other sources or demand. The overarching vision is to create an intelligent, smart grid that substitutes AI for many manual reactive tasks, achieving high efficiency, greater dependability, enhanced affordability across the entire energy supply chain.
A self-healing grid, almost.
That's the goal. A grid that can self-heal, reroute power, anticipate problems before they occur. The key insight is that AI is the essential operating system for a modern, resilient, decarbonized grid, capable of managing the unprecedented complexity of integrating diverse and intermittent energy sources.
And AI isn't just making existing systems better, it's also speeding up the creation of entirely new energy technologies, right? The pace of innovation in areas like advanced materials is absolutely critical for meeting our climate goals.
This is where AI truly acts as an accelerator for energy innovation, potentially leading to breakthrough discoveries. The rapid development of advanced solar PV, next-gen batteries, sustainable biofuels, it's crucial, and AI is dramatically speeding up the material discovery and design process.
How does it do that?
Consider medicine. AI led to a phenomenal 45,000-fold acceleration in discovering 3D protein structures. Similar potential exists for energy materials. Take perovskite materials.
Is solar cells.
Exactly. Immense promise for cheaper, more efficient solar PV. Yet the number of possible chemical combinations is astronomical. Less than 0.01% have ever been physically tested in labs.
Wow.
AI can rapidly sift through vast data sets of material properties, predict promising new compositions with desired characteristics, simulate their performance, compressing years of traditional lab work into months or weeks.
Accelerating discovery.
Massively. AI also helps integrate these innovations into complex products and supply chains. A modern battery gigafactory, for instance, can produce an astonishing 10 billion data points per day.
10 billion a day.
Yep. AI can analyze these immense data sets in real time to detect subtle faults, predict long-term performance, diagnose problems, optimize manufacturing, reducing risks, costs, and timelines for innovations to reach market.
That's incredible. Any other examples?
Sure. Even in transportation, Google uses AI in maps for fuel-efficient routing. They estimate it's prevented about 2.9 million metric tons of greenhouse gas emissions since launch. That's like taking 650,000 cars off the road for a year.
Just from smarter routes.
Yep. They're even using AI to help pilots avoid creating contrails, those white lines in the sky, which are actually a significant, often overlooked contributor to global warming.
Helping pilots avoid contrails. Wow.
Yeah. Despite all this immense potential, AI-first approaches are currently underrepresented in energy innovation. Only about 1% of energy-related patents and 2.3% of energy startups explicitly reference AI.
So there's still huge untapped potential there.
Vast, largely untapped potential. It suggests the integration of AI into energy innovation is still nascent, but holds the key to dramatically faster progress. The key insight is AI acts as a scientific multiplier, compressing discovery timelines and optimizing complex processes, making it indispensable for engineering the future of clean energy.
So what does this all mean for you, our listener, as you navigate this rapidly changing world? You can see that AI's energy footprint is, well, undeniable, and growing at an incredible, unprecedented pace. It's creating both significant environmental and grid stability concerns that we just can't afford to ignore. But this deep dive has also revealed the sheer ingenuity being applied to the problem. From groundbreaking hardware innovations and algorithmic breakthroughs to AI's inherent capabilities to optimize and innovate. This collective effort presents a clear path forward that could genuinely redefine our entire energy landscape.
If we connect this to the bigger picture, we are truly witnessing the collision of two core revolutions of our lifetime:
Yeah.
artificial intelligence and the global transition to clean, renewable energy.
Right.
This deep dive has shown us that AI is simultaneously a significant driver of increased energy demand and a profoundly powerful tool that can help us navigate the immense complexities of the clean energy transition, optimizing grids, discovering new materials.
The paradox.
Exactly. The paradox of AI and energy is not just real, it's a defining challenge of our era. And how we manage it will profoundly shape our future, impacting everything from the resilience of our power grids to our collective ability to meet global climate goals.
It really does feel like a generational stress test, doesn't it? Forcing us to reimagine not just how we generate and consume energy, but how we use the grid itself, moving towards a far more flexible, dynamic, and intelligent system.
It does.
The journey ahead demands crucial transparency from tech companies, smart and adaptive policy from governments, and relentless continued innovation across hardware, software, and grid management. It's a truly dynamic field that will undoubtedly continue to evolve rapidly, presenting both challenges and incredible opportunities.
Which raises an important question for you to consider, one that we all really must grapple with. As we build more and more powerful artificial intelligences, what kind of future do we want to power with AI?
Hmm.
How can we ensure that the intelligence we build also actively builds a more sustainable, equitable, and resilient world for everyone, not just for some?
The perfect and critical thought to leave you with, and one that resonates deeply with the spirit of the deep dive. Thank you for joining us on this extensive exploration into the fascinating and urgent intersection of AI and energy. We hope you feel significantly more well-informed and perhaps even a little more curious about this critical nexus of technology and sustainability. Until next time, keep digging.